Yo, okay. So this video, let's talk about Gaussian mixture models and EM. I think to me, was very confusing. It is still kind of confusing, so I'm gonna try my best. I think there's just like an incredible amount of notation to understand here. So I'm gonna do my best to build up the intuition slowly and build up the notation slowly so things kind of make sense. So first, we're going to start with like what is Gaussian mixture models, and then I'm going to show you like all the different equations and then how they build on each other, and then how you use EM to get what you want, get the output. But first, let's understand like what is going on here, like what is the problem setup, and then what is like the final output. So first off, let's just start with an example. So let's just take a one-dimensional example. Okay, yeah, sure. So let's say this is height. And so we have two clusters. So the point of Gaussian mixture models in EM is clustering. So you have data, it's unlabeled, and you have no idea what the correct labels are. But you know you want to separate them into two classes. So that is clustering, and this is one way to do clustering. And so a very popular way to do clustering is like k-means, and this is a more complex way of doing something very similar to k-means, but you get more out of it. And that's kind of the high level. So we're doing clustering. And so here we have an example. We have height. We have a bunch of observations. And it's GMM, so Gaussian mixture model. And so let's say we are going to assume we have two classes. So the first bit of notation is that k equals 2 because we have two classes. And so let's say we observe like from male and female. So there's probably going to be like two different Gaussians. So maybe the smaller people are the females, and the taller people are the males. And so we want to fit two Gaussians to this data. And we don't know which Gaussians are the best, and we don't know how to assign we don't know which class every data point came from. We just have a bunch of data points, and now we want to fit two Gaussians. So that's kind of the point here. So we have k equals two classes, and so then we want to find parameters for our output Gaussians. So that's one thing that we're going to output is these parameters. So we're going to have like mu1 and sigma 1 for the first Gaussian, and then we're also going to have mu2 and sigma 2 for the second Gaussian. So this one will be for this Gaussian, and that will be for that Gaussian. So that, we know where the Gaussians are. And then we'll have we'll have assignments, like we'll have data point X belongs to some class 1 or 2. But we'll also have something more rich than that. We're going to know, so here's a bit of, we're going to know what is the probability that each data point belongs to either class. And so it'll be like 0.3, 0.7. That's kind of what it will look like. So instead of just saying it's certainly in one class, we're going to have a probability distribution over the potential classes. So the notation for this is let's see, probability E1 given X, something like this. Okay, and we'll get to that notation, don't worry about it. But the main point is that we output probabilities for each data point. So each data point has its own list here of probabilities that belongs to either class. And so we can set k equal to whatever we want here. It can be as many classes as we want, but is height, so maybe male, female. Maybe we have 3 classes, whatever. Now that we have our problem statement and what exactly we're outputting, it's time to actually take a step back. Okay, so we're dealing with multiple Gaussians, but let's take a step back and see what it was like if we only had one Gaussian. So we have a bunch of data, and we want to find the Gaussian with parameters that is best for this data. So you've probably seen this before, but it's good to go over this because this actually is like very similar to the final answer, which I guess isn't super surprising. Okay, so let's start with the probability of one data point given the parameters is the equation for, let's do a multi-dimensional Gaussian. Okay, so it's like 2 pi so d is the number of dimensions. So this is super ugly, okay? But this is the likelihood of one data point given the parameters. And so the log likelihood makes this a lot simpler. And then we okay. So we get, it's like something real ugly. Yeah. Okay, so that's just taking the log of this, nothing super extraordinary here. And then so we want the likelihood over the whole data set. So then we're just multiplying over the whole data set. So right, and then that's just that. So, and if it's the log, then that becomes the sum over all of those things. So then now we want to solve for the variance, the mean and the covariance. And so you end up getting right, that makes a lot of sense. And the variance you use the answer for the other one like this. Okay, perfect. So that is the MLE solution for just one Gaussian. So if k equals 1, this is actually the easier way to do it. And so this is saying is, given a data set, what is the best parameters for a Gaussian we can have? Okay, so remember these equations. We're going to come back to them. But now it's time to look at Gaussian mixture models. Okay, so the story with Gaussian mixture models starts with the idea that, all right, so we start with the idea that every data point has this hidden variable z. And so if we knew z, then we would know what class this belongs to. So z, for example, equals 1, 0, 0, and this is for 3 classes. We'll do 2 classes that we had before. So this tells you that this data point belongs to class 1. And then maybe this z tells you that this second data point belongs to class 2. So if we knew this, and if we took a hard stance on this, then we would basically be doing k-means. But the point here is that we don't know this, and we're going to assume that we never truly know this. But it's going to be helpful to derive the rest of the equations. So we're starting off with z, and z is one-hot encoded and is latent, meaning we will never know it. But we're going to be using it as we build up the rest of the equations. So if zk, this should be, if zk equals 1, then that means data point 1 is in class, or is class k. Okay, cool. So now let's move on. So now we're going to really get into it. So we wanted to find the likelihood of the data point given the parameters, right? So, but we have this latent thing. So it's going to be x and z to start off. So before we were doing just Gaussian, it was p of x. There's like p of x given theta. But now we're going to have to augment it and do pxz. Okay. So by definition here, it's kind of going to look like this. So let's try and solve for what this actually means. So here we know that this is like a one-hot encoded thing. So the prior, this is like our prior. So this equals, oh shit, okay. More notation here. Okay, let me break this down. Okay, so here it's iterating over all of the classes. And so it's, but we need to define this pi thing. Okay. So pi of k is the prior likelihood of class k. And to start off, like maybe it's just like uniform, but we're gonna make it better over time. But basically it's just saying like we have 2 classes. If you're gonna sample something, so now so pretend we have these 2 distributions. If you're gonna sample a point from this whole thing, well, you're gonna just pick a distribution, or pick one of these at random, kind of, or pick one according to the probability, and then sample from that. So this is the probabilities. Okay, and then we're just multiplying them all together, and raising it to z, because then this is really just pi of k, where zk equals 1. Okay, and hopefully that makes sense. Okay, so now this thing. So the probability of x given z, and given zk equals 1, so given it's in this distribution, so given this is the correct distribution, then it's just the normal the whole thing here. All right, hopefully that makes sense here. So given it zk equals 1, then it's just the regular Gaussian formula for the probability of x. You plug in x and the parameters for that Gaussian. So now we have both of these things and we can combine them. So the probability of x and z, the joint distribution, probably k equals 1 to k. So we're going through all the different classes, and it's this. We're just combining these two things together. And so we'll get, so this is like a trick that you got to get used to. So zk is ever only 0 or 1. So this means that this whole expression is either this exactly or it's 1. And so this whole thing will like evaluate whenever zk can only be once. Once. So this means that this is like only only true for like when zk equals 1 and not correct k. Okay, so that's the joint distribution. And now we want to get rid of the z here in the joint distribution by marginalizing. So px equals, so we're just marginalizing this. We want to get rid of the z. And so we know that only one zk can be 1. So this means that this is going to simplify. And then we get probably k equals 1. And k. So this simplifies to this. So now we have the probability of one data point. And so this equation is very nice. This is saying if you go over all, so we want the likelihood, we have one data point, and we want the likelihood of that data point. Well, we're going to look at each Gaussian and then get the likelihood for that Gaussian, but then we're going to weight it by how likely it was for us to pick that Gaussian. And we're going to do that for all of them, all the Gaussians, all the classes. So this is like an important equation that we're going to keep using. Okay, so now one more important thing here is this called like the posterior. And this, so it's got this notation. And this is just hiding notation that really means this. So up until this point, we were doing pxz, px given z, but now we're flipping it. And we'll see why in a second, because this is the posterior. So we're thinking Bayes' rule. But this is saying, what is the probability that the data point belongs to class K? What is the probability that zk equals 1? Right? Because if z equals 0, 1, you're asking what is the probability that z2 equals 1? And what is the probability that it belongs to class 2? Okie doke. So, right, so I said Bayes' rule, that's basically what's going on here. So we know how to do this. We just defined how that works. And we also just defined how this works, which is very nice. And so it's a similar idea down here, just summing over all the classes. So this is Bayes' rule, and this tells you how to compute that. And so we know how to compute this, which is great. So that means that we can compute these posterior responsibilities. So we now know like how to compute. So we now know how to compute px given zk equals 1. We now know how to compute p equals 1. And we also know how to compute p zk equals 1 given x, which is the same thing. People just use this notation of z. Okay. All right, so that's a lot of notation. But these are the three equations that we need to be able to compute. Great. And mainly because this is what we need to compute. Because this is like our final output, right? This is telling you the probability that for one data point, this is telling you the probability it belongs to each class. So you could think of like the output for data point 1 would be like Z1 and yeah, it's like the probability for each class. Okay, awesome. So now you could think like, okay, so we have the probability that we have the probability of x for one data point given the parameters, which is this, probably k equals 1, probably k. So it's very tempting to be like, okay, we have this. This is the likelihood for one data point. Why don't we get the likelihood for the whole data set as this, right? And then we take the log likelihood. But something is very sad and bad is going to happen here. So this looks good, but the log of this is the log of this. And you're taking the log of a sum, which is bad news because you can't really solve it directly and get an equation like you had, like probably you've done in MLE for just a regular Gaussian. So we need a more complex tool. And that tool is expectation maximization. And so we have all the tools we need already. So hopefully this isn't too bad. So expectation maximization is iterative, and it involves two steps and then build on each other. So you do the E step, and then you use that to do the M step, and then you use that to do another E step, and then you use that to do another M step. And you'll see what I mean here. So the E step. The E step is when you calculate all of these responsibilities for every data point, because we'll need this for later. We'll actually need it in the M step. Okay, so the E step is calculating all of these. You need to calculate these for every data point. So we have x1, and then you need to calculate it for every class. So 1, and you can see this is kind of a lot. Z11, Z12, right? And it becomes like this whole matrix of these outputs. But this is very important. This is like basically like how you do your predictions. So you calculate all these in the E step using the equations that we just defined, right? We're using these. So this uses these two in Bayes' rule. So we don't how to calculate this. So, technically we can just output this and be done. But this is not going to be a very good output. We need to because these use these parameters. But these parameters initially are just bad. Like, we probably randomly initialize them. So how can we trust these to help us do this, to help us do this, and help us output good this? It's not going to work. So now that we have this, we can estimate better parameters. And so then we go all the way back to like 30 minutes ago to these equations. And so your new parameters, you update them using these equations, which we had already basically derived. So first of all, so the new mean, so mean t plus 1, because we're in a new iteration. So the mean for that class is this. Okay, so the only new thing here is this, and that comes directly from the E step. So that's the only thing different than the Gaussians before. And so it's the same thing for the covariance. You just stick in this new term because you're weighting it by the new information that you have. Okay, so that's the mean and variance. So the only thing you have new is this. You just put that in there. And then you also have one more term that you want to estimate, which is pi k. This is like one of the first things that we did. You want to make that better too, and so this is just saying the number of things in class K, and then like the number of data points. So it's just like the probability that if you're going to pick a class, you would pick that class. Cool. So then now you have better parameters. So then we can do the E step again and calculate these again, which, once again, if you want to calculate these, then you need these. And then to do these, you need to use the Gaussian equation with those parameters. So now we have better parameters, so we can make a better prediction and final output for that. So now we have a better this. And then we do M step to get better parameters. And you keep going, and you calculate this every time to see if it converges. And that is GMM with EM. And all of the crazy notation. All right, nice.